All right, the purpose of this video is going to be twofold. First of all, I want to go through the worksheet that is entitled at the top, Worksheet Electron Configuration. I just want to make sure that the students have, or that you guys have, a strong knowledge about these basic questions and these basic things. So number one says, within any given shell. And what does that mean? It means the subshell of energy. How do the energies of S's, P's, D's, and F shells compare? So that's number one. Well, this is a pretty simple one, okay? So S's generally, which are spherical orbitals, have less energy than P, have less energy than D, have less energy than F. Now that's a general thing because as we go to different quantum energy levels, these can differ. But within one energy level, so like the first one where all these show up is, 4S, 4P, 4D, 4F, it would go S, then P, then D, then F. If we're looking at different levels, then they can differ, in which we talked about before. But generally it goes S, then P, then D, then F. Number two says, within a subshell of P or D or F. By subshell, what do they mean? They mean this. If you have something that's 3p3, means you have 3 electrons at the 3p level. And it says, how do the energies of the orbitals compare? Well, if you were to look at these electrons right here, those 3 electrons, since they're all 3p, they would be the same. And that's what I'm trying to get across to you. Is if you were looking at, 4d5, and you're looking at these 5 electrons all located at 4d, again, the energy would be the same. Okay? Number 3 says, what is the Pauli exclusion principle? This is a pretty simple one where we just need to know the definition of what Pauli says. And what Pauli says is, Pauli says this. Pauli says that in an orbital, you can only have 2 electrons. So, Pauli says 2 E- electrons per orbital. Number 4. That's called the Pauli exclusion principle for its long name. Okay? Hund's rule is number 4. Hund's rule says this. Hund's rule is kind of a fun one. Hund's rule says that electrons will fill empty orbitals first. Now, the analogy I make with this one is to think of it like rooms of a house, right? Okay, so if you had, a 3-bedroom house and only 3 people lived there, everybody would take their own room, theoretically, right? That's what Hund's rule says, is that electrons will fill empty orbitals first. They're not going to take a roommate unless they have to. Number 5, what is the Aufbau principle? And what Aufbau says is this, that we will fill in order of lowest quantum energy level to highest. So electrons will fill lower energy orbitals first. Now, I said that a little bit funky just now, and I want to make sure I get it right. Because sometimes it isn't the quantum energy level. For example, something like 3D versus 4S, right? Well, when we do electron configurations, you're going to find that you place the 4S before you do the 3D. And so what ends up happening is these actually have more energy, right? But they're located at the 3rd quantum energy level versus these that are at the 4th level. So, 1, 2, 3, these would be located in the 3rd level versus the 4th level, yet these ones in here have more energy than the 4S's do. Remember that was that whole idea of when we talked about how, the Heisenberg uncertainty principle and electron configuration helps to disprove this idea of Bohr saying energy increases as you move away from the nucleus. Not true. And so what ends up happening here is Aufbau would say this: since the 4s have less energy than the 3ds, the 4s's will fill first. That's why it goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Because these are the orders of increasing energy to fulfill Aufbau. All right, the next thing I want to talk to you about is something called electron orbital diagrams. Number 6 says how many unpaired electrons will be found in the ground state, and it says you'll need to draw the hotel. Now, I use an analogy of a hotel to symbolize this thing called electron orbital diagrams. So number 6 is an example of one, and we're going to do it together right now. So the first thing we have here is it says the element is magnesium. It is not charged, therefore it is just simply magnesium. You go to the periodic table and you find the atomic number of magnesium, which is 12, meaning it has 12 protons and 12 electrons. Because this is electron orbital diagrams, we only need to know the electron number, and it is 12. So if we were to do the electron configuration of magnesium, it would go 1, S2, 2, S2, 2, P6, 3, S2. Now we could go to the periodic table, find the third period, go over to the S block, find the second element, it was in DP, magnesium. Okay? I've got a periodic table right here, so we can do that. Right? So 1, 2, 3, the S blocks are here. S1 is sodium, S2 is magnesium. So there you go, a little review of the checking method we do in class. But this is called orbital diagram. So what we do is this. You draw an axis. And this axis represents distance from the nucleus. Now remember, those numbers refer to distance from the nucleus. And what do I mean by that? I mean this. In this electron configuration, energy is increasing as you go from left to right. It always is. That's Aufbau's principle, right? Aufbau says that they'll enter lowest energy orbitals first. So they start with 1 and they move all the way to 3. And then we keep going if necessary, but we only have 12 electrons here. Okay? Now, the first thing we need to concern ourselves with is something called Pauli's exclusion principle. Can you have a minute? No.
Yeah.
All right. So Pauli's exclusion principle says this: that you can only have 2 electrons in an orbital. Now, just like in a hotel, you enter on the first floor. So you always start at number 1. That orbital is an s orbital. S orbitals, at most, there are 1 of them. And because of the exclusion principle, Pauli's exclusion principle, you can fit 2 electrons in it, right? So we needed 2, so we put them in. 1 up and 1 down. Now the reason we put them up and down is because electrons are both negatively charged, right? So Coulomb's law says that negatively charged things would want to repel each other, right? So the problem with it is we're trying to take these 2 electrons and put them in the same room, the same orbital. And so what happens here is one of them says, okay, I'm going to spin, and we symbolize it with a positive, clockwise. And likewise, another one in a downward is going to be counterclockwise. So this way we could still keep Coulomb's law intact. Okay? So then we keep going. We get to the second level. And at the second level, there is 1 s orbital. Why? Because s's always only have 1 orbital. How many electrons fit inside of it? 2. You put the first one up, second one down. Brings us to another thing located on the second floor of our hotel, or the second energy level, quantum energy level. And it is P. There are 3 orbitals at the P level. P of X, P of Y, and P of Z. We drew them on an axis for you a while back, if you remember. It looks. All right, I wanted to switch markers. So I was talking about P of x, P of y, and P of z, right? We have 3 orbitals. Each could contain 2 electrons. The person who says that is Pauli's exclusion principle. 2 electrons, 2 electrons, 2 electrons. Well, if you looked at, the axis of these, right? P of x would be this one. And it looks like a figure 8. 2 electrons could be in it, right? P of y, 2 electrons could be found in it. And likewise, P of z with 2 electrons in it. 1, 2, 3, 4, 5, 6 electrons total. Not a coincidence that it matches the 6 right there, because we needed all 6 of these to be there. Now, what Hun would say is this. When you go to fill these, right, 6 will fit 3 orbitals with 2 electrons each. The first 3 would take their own room, according to Hun again. But what ends up happening is, that's this electron, but that electron is still there, and that's the Z one, right? So we'll put it there. Then, let's say that electron is that one right here. Well, there's that one right there, so that one's there. And then your last one is your Y's. So what you end up with is 3 pairs, which makes sense with 6. Last thing is, okay, so you have your 3. The first always goes S, then P, then D, then F. So we have S. 1 orbital at the S level always. Notice that is a trend. 2 electrons, well, Hun would say one of them would try to take its own room. But, oh, there's a second one. So another orbital goes in here, or another electron, I should say, fits in this 1 orbital. So to finish the question, how many unpaired electrons are there? Well, this is paired, paired, pair, 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 pair. So the answer to question number 6, how many unpaired are there? The answer is 0. There are no unpaired electrons. But let's do 6b now. 6b says the element is now phosphorus. So when you go to phosphorus on the periodic table, you'd look for it and you'd find that there are 15 electrons in it. Okay? It is not charged, it's not an ion, therefore it's just the atomic number, which is 15. Well, that's 1s2, 2s2, 2p6, 3s2, 3p3. 2, 4, 10, 12, 15, 15. Matches. So here's the orbital diagram. Distance from the nucleus. So I write in distance. We always start at the first level of the hotel. S orbital, 1 orbital at any S. How many electrons will fit inside of it? 2. 1 up, 1 down. Next, second floor, second quantum energy level. S orbital, always just 1 of them. Up, down. Why? Because there were 2 electrons. Then at the P level, we're still at the second quantum energy level. At the P level, there are 3 orbitals. P of x, P of y, P of z. Px, Py, Pz. Up, 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 because Hun says they'll take their own, but we got to get to 6, so down, down, down. Then we get to the third quantum energy level, which is 3s. 1 orbital, up and down, because there are 2 of them. Which brings us to this last one, 3p. And at the p level, again, there is always 3 orbitals. Sometimes they're occupied, sometimes they're not. Well, p of x, p of y, p of z. We only have 3 electrons to place here. Well, here's what happens. Own room, takes its own, takes its own. I call them rooms, but they're orbitals. So what ends up happening here is in the very furthest level, you would have something like this. You would have an x orbital at the third quantum energy level. So it would be the third biggest one, and there would only be 1 electron in that one. And then you'd have a y, and there would only be 1 electron in it. And you'd have a z, and there would again only be 1 electron for 1, 2, 3, and 3. And that is the orbital diagram for phosphorus.